8, and that will wrap up. Oh yeah, I'll do 8, and I'll wrap up the whole session because I need to go. Some people have come into office hours talking about there's a homework question or a practice exam question where you have a rod and a bob at the end, and the English is a little bit poor in the question. It says that the bob and the rod each have a mass, or they both have a mass. I think it's both have a mass, but you don't know whether that means some of them are equal to a certain number or that they each have a mass. So I just stated here they have, one has a mass of 550, the other has a mass of 550. So this is about a physical pendulum and comparing it to a simple pendulum type question. And I want to talk a little bit about moments of inertia, adding moments of inertia, those kind of things. So I'll focus here on the physical pendulum. So it's constructed of a rod of length L, and then it's got a bob of mass down here at the bottom. So we didn't do a lot of stuff in moment of inertia, at least for those I'm speaking to that took 114 with me on moments of inertia. Our textbook doesn't really get into it. But if you have an object that consists of, two separate objects, the moment of inertia of the combined object is the sum of the moments of inertia of the individual. So I'll do like the I of the pendulum is going to be I of the rod plus the I of the bob. So you can add moments of inertia, basically, is what I'm saying. And so the physical pendulum, I have a rod. So a rod that's pivoting about, so say it's pivoting somewhere, didn't it? The rod rotates about the end opposite the bob. Is a known quantity. So that's one, if you could look up in a table, 1/3 ml squared. So if you just Google like moments of inertia of a rod, they'll give you one about the center, 1/12 ml squared, about the top end, one of the ends, 1/3. And the bob is the easiest of all. A mass at the end, the mass, rotating mass about a point is just its mass times the distance squared. That's how you sort of start with moments of inertia. And this is basically mass rod plus mass bob. But what's nice here about the homework question is that the m or equals the m bob. So that's what makes this nice, that you can combine the two m's here. So if m or equals m bob, then I can combine this into 1/3 plus 3/3 is 4/3 ml squared. And this m can represent either the mass of the bob or the mass of the rod. Okay. Now I would have to tell you that, and I don't expect you to know that in an exam question, but I would have to tell you. Okay. The other thing what we don't know here is the distance d from the center of mass of this object. But because the two of them are the same mass, the center of mass of the rod is right smack in the middle of the rod, because I'm assuming it's a uniform rod, I should say that. And then the center of mass of the bob, or center of gravity here, wherever I interchange those two, is right here. And they each have equal mass. So you can imagine as if I compressed all of the mass of the rod into this point, and then we're in a sense trying to think about this, the combined center of mass. Where do you think it would lie? In the middle, right? Between the two. So this is the center of gravity of the pendulum. Now you can do a center of gravity calculation, m1 y1 plus m2 y2 over the sum of the masses, but if you hold something that's equal masses, like a dumbbell or a barbell, the center, if you wanted to balance it, you'd hold your hand in the middle of the barbell, right? So that means that the distance d in the equation is going to be 3/4 L. All right. So this is a bit of a beast of a question. So the period of this, period of the physical pendulum is 2 pi root of I over mgd. And there's one more tricky part to this. So the I is 4 towards ml squared. So I'll keep the 4 on the top and the 3 on the bottom. But the m on the bottom is the total mass of the system, of the physical pendulum. So I use the single m over here because they're both the same. But the m in the bottom is, so this is mass bob or mass rod, this mb, this in moment of inertia, which means that if I want to cancel out the m's, I would have to have 2 mb here, or 2 mr, but they're the same mass. G, and then this times 3/4 L, so I'll leave the 3L down the bottom and bring the 4 up to the top. Kind of regretting this question now. Okay, so I get rid of those MBs. I get rid of the L on the bottom with the square term on top. And I'm left with, I can take that 2 down there, we'll make a 2 up on the top. So that's 8 over 6, right? Which is 4 over 3. Oops. 4 over 3 L over G. Right? Did I do it? Oh, 9. What am I saying? 3 times 3 is 9. 8 over 9. Sorry. Getting tired. 8/9 L over G. So, in a sense, in most cases, the period of a physical pendulum can typically be described as the period of a simple pendulum of some sort of length. So if we had, like that was the whole demonstration. So if we had a simple pendulum that was 8/9 the length of this physical, they both would oscillate with the same period. Because this is the length of the physical. So if I had a string, with a small bob at the bottom, 8/9 the length of this physical, they both would oscillate in sync. So that's sort of where what I would do for this last part is determine the length of the rod if it is known to have the same period. So the very last step, this question would not be exam level, just before you get worried. But individual steps, physical pendula, all fair game. So I'm trying to find the length. So again, the L here would be equal to t squared times g times 9 divided by 4 pi squared times 8, right? So if square everything, bring the 9 and the g up, bring the 8 and the 4 pi squared down, and then just set, the t equal to the 12 over the 15, and you're good to go. I don't know what the answer is. I didn't get time to solve it. But the period is, what is it? It's 4/5 of a second, right? 12 over 15. 4/5 0.8. Okay. I need to go.